let's carry on with the official stuff. By the way, the job fair is coming on Thursday, so go to that if you were interested in getting a job. It'll be online, and my Thursday class will start an hour late, so everybody has time to attend this whole thing. I don't know how many employers we have or anything, but in the past, before the pandemic, this was a great event with more than 100 students, 10 or 15 employers, many jobs. Many people got jobs right on the spot. So I don't know how much of that will be at this one, but it has been very valuable. Even students who are not ready to get a job yet often benefit from going to this thing to hear descriptions of the jobs and the skills that are needed. So anyway, check that out. And here we are at 127. And what we're going to do is talk about heap overflows, but first I want to finish the format string, because when I tried to demonstrate it last time, it failed right at the end, and now I know what happened. So let me just bring up my Debian machine, and let's go here, and CD chapter 4, I think, is where it all is. All right, and let me bring up some instructions to talk about this. So this is the project, ED204, which is the simple format string vulnerability. And I updated it to Python 3, which is one thing I wanted to do. And I also figured out why it crashed right at the end. So let me just go through the Python 3 version, which is the only one we're doing. I mean, there's no reason to use Python 2 anymore. It's out of date. I just did it because I was befuddled by other problems enough not to do it. So the Debian machines have Python 3 already installed. All you got to do is type Python 3. And there you see it. So I'll exit. All right. So the program is ED204. ED204.c. All right. Gonna make that bigger. All right. So here's the program, and this program has a main routine, and here it copies the argument from the command line and puts it in something called buff, and then it just prints it with no format string. So if that argument should happen to contain a format string, you can print it here. That's all it does. And so the point is we want to exploit it. And when it gets to this exit command, we want to hijack its call to the system library call exit and make it go somewhere it's not supposed to go. That's all we want to do. So if you run it right now with ED204 and hello, if you give it normal text, it just prints back the normal text. But if you give it, say, %x, then it begins to print data that's coming off the stack. And if you give it %n, then it will print right to memory and crash, of course, because it's wrote to some uncontrolled area of memory. I didn't carefully choose a location, so it chose an invalid location and crashed. So that's the game. And so there are some exploits. And here's the simple one to write 4 bytes. And the only difference in Python 3 is you put Python 3 here instead of Python, and you import sys, because outputting non-printable characters in a print statement is something you can do in Python 2 and in C, and it's actually kind of a stupid, awful thing, and modern languages won't let you do that. It doesn't really make any sense to output things that are not valid characters and print them. So what you do is you use sys standard out buffer write, and then you write byte streams, and this will send raw bytes out to the standard output. But that's really not printing printable characters. This is how you do it. Everything has to be byte strings, so instead of putting in quotes, you put a B in front of it, and then you have to use the sys write command instead of print to print them, and then you can output raw bytes. So let's see how this one works. Here's F1. I think I've already got it. Yeah. So it creates these 4 write things, which have 4 bytes, which is an address to write to, and then just 4 characters. I put junk. And then down here it has all the format strings for all that, which will cause these addresses to be used in the %n statements, and it will write with those 4 %n's to those 4 addresses. And so if I run this thing, F1, here it is printing out that stuff, and some of that is unprintable, like 0804, A014. So if you want to see it in all its glory, you run it and then pipe it to XXD. That'll print the hexadecimal version. So now you can see here are the characters 0804, A014 are these unprintable characters here. So you can see exactly what it's putting out. And now, if you run that in the debugger, so GDB minus Q ED 204, and then run the output of that thing, that ended up going to this address, 30, 38, 40, 48, and that address went there because that is the new address of the exit, which you can see here. That's the pointer to exit.global offset table, program linkage table, and that has been overwritten by this address, 30, 38, 40, 48, because it had printed 30 characters at this point, then it had printed 8 extra characters to do this, so next one was 38, 40, and 48. So now I can print a stupid number and make it crash. So to gain control over it, you need this one, which is F2. So quit, yes. All right, so now I have the same old stuff, import sys. Here's the 4 places to write. Here's the things I want to write in, AA, BB, CC, DD. And here's what you have to do. You have to add 256 times a different number each time, because every time it prints, the value it prints is the total number of characters so far, and that can only get larger. So the only way to reach an arbitrary number is to make it bigger than 256 so it can roll over and hit any number you want. And so the least significant byte of this number will be any number you want. And there'll be a more significant byte, so when I write it here, it's going to write to byte 14, and it's going to write uncontrolled numbers to the other bytes. Every time. Each time I write, it'll write 3 extra bytes of collateral damage I don't care about. So I'll write to 14 and junk, 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 write to 15, junk, 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 write to 16, junk, 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 and write to 17, junk, junk, junk. So after 4 write operations, I have written an entire 32-bit word of my choice, plus done some collateral damage past there that I don't care about. And that's the game here. And this is what you have to do. You have to make the numbers and then turn them into strings and then encode them with Latin 1. This is how you get back to raw bytes in Python 3. At least it's the best way I could find out how to do it. And now you can use this thing, sys standout buffer write, to write it out. So if I run that one, that's F2. And it's kind of hard to read. Let's put it in XXD again. All right. And so now you see these big numbers. 385 is the length of this 385x%n. That is going to make print number 2 memory, and it's going to, this one, %385n. %385x is going to write a word, and it's going to make it 385 characters long. So it's going to be padded with 378 spaces. But the point is, that's how you make the total number of characters so far keep changing. So there's going to be these 4 numbers that are all over 256, which are chosen to make the least significant digit turn into what I want. And so if I run that one in GDB and run with f2.py, then you see it worked. The instruction pointer ended up being AABBCCDD, which crashed. And I could check, it did do that, of course, by overwriting the exit pointer, which is there. So now I put in this arbitrary number. So now F3 is only dummy shellcode. We did all this last time. So here I make a NOP sled of 100 NOPs and then 250 breaks. So I've just made some fake shellcode. All the rest is the same, even with the AABBCCDD numbers. So now I write that junk out. So after that, I put NOP sled and shellcode, just it's going to appear on the stack somewhere. And I don't really know where. And so now I have to run this to find out where I'm going to find my shellcode. So I go back into GDB and run F3. And now I do info registers would be, and I can see the stack starts here at FFFF CFDC and it ends at D3F8. All right, so I can X 100X ESP, and here's my NOP sled, and here's my fake shellcode. So now I can see if I just put in any address in this region, it'll be okay. And I usually just go to the middle of the region just to make it reliable. So if there are small changes, so here's a pretty good looking address, D05C. If I jump to that address, then it will be likely to work. So let's just copy that D05C. And I think I put that in, did I put that in F4? Let me see what I did. Oh, I put it in F4. Good, it's already there. Okay, good. So let's cut out of here. Whoops. And look at F4. All right, so there it is, D05C, FFFF, D05C. That's all I do is put those bytes in here in reverse order. So now, when I run this one, dollars, F4. Now it hits a break trap. And if it stopped at this address, and if I want to see it, I can do X100X, ESP, and I can verify that what it did was it hit the NOPs, and it went nop, 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 nop until it hit this break and stopped. And that break is, this is HC, this is 90, that's 95, and you can see that's right. It stopped at D095. So this proves that I have controlled the instruction pointer. I have pointed it to code I injected, and the code I injected can execute because these NOPs executed. If there had been data execution prevention turned on, stopping you from executing code in the stack, this would not have worked. But there isn't. So I do have the ability, I've now gained code execution. So all I have to do is put in better code. And this is where it failed last time for a reason which took me a while to figure out, but you're going to see why, more or less. So we won't worry about bad characters. That turned out to be fine. The only problem was the shellcode. This is the command we use to make shellcode. And I'm going to try doing it, well, if I run that command here, let me show you something. If you run Metasploit commands to make shellcode, let me adjust my window so it doesn't wrap out of the visible screen. All right, it's different every time you run it. There, this is BF F6 B2. If you run the same command again, ADCDBA. It's different every time. You can see it at the end. E9, 96, 6B, totally different numbers. So you get, now these, none of these numbers have avoided the bad ones. 0, 9, A, D, and 20. Those are forbidden. And that I thought would be enough, but it turns out that is not enough. When I ran it, that pattern of bytes crashed before it did the exploit. So if I go back into my GDB, and then I do list, here's what happened, which I didn't catch last time. Here it does the string copy of the command line argument into the buffer. Here it prints the buffer, which is what is the format string exploit that changes the address of exit. Then it goes to print here, and then it does exit. Now, the normal problem is when you print it, if you have bad characters, it won't all go into the memory. So it'll still do this, it'll still exit, but when it tries to run your shellcode will be only going halfway through and then broken. But this one crashed on the print. I don't know why, but somehow I got a pattern of bytes which crashed the C print command. Which I don't even understand how there can be a pattern of bytes that crashed the C print command, but they did. So the cure was to just run MSF Venom again and make different shellcode. So I didn't save it. I could look at the video and look at it, but anyway, that's I don't know how often that happens, but I just tried running again, and I've tried it like 3 times since. It works most of the time. So this has got me a lot. These Metasploit payloads have strange side effects. Anyway, so that's it. And so if you just run it and take this payload here, these Python commands, you can stick it in your final exploit, which is, I think, F5. Well, let's see. Yep. Oh, it's f5.py. All right. And so this is all the same. Here's the same address, FFFFD05C. But now, after the NOP sled, I create the buffer, and then I calculate padding, which will just take bytes of A and fill up enough to make the padding plus the buffer be 250. And now I write NOP sled, the buffer, and padding here. So if we run this one in the debugger, which is F5. Well, first, let's put a breakpoint in. And we can do this in source code, actually, which is the way I think maybe I should have written this project. We do have source code debugging. So what I'm going to do, here's where the format string overflow happens. So I'm going to put a breakpoint at 14 and a break at 15. And now, if I run it with input coming from F5, okay, it hit the breakpoint, so it has not overflowed the buffer yet. So I can check the value of that address where the pointer to exit is, and it should be unaltered at this point. And it is unaltered. It's pointing to 08048366. That's a reasonable looking value, probably going the right place. And the now if we continue, then it does the overflow, and that should have changed that value. And it did. It changed it from 804 to FFFF D05C. Now, if I do X100 X ESP, here's the D04C here. So it's hitting the NOP sledge. So now I can do next I. Oh, that'll go to the next line of source code. All right, I'll do one more next I. EXT. Okay, and that's now ready to do the exit. And now if I do, let's do info register. You see the instruction pointer is here at main plus 131. Now I'm going to do the exits, which is step I, a single screen language instruction, and keep doing that. There. Now I've entered this exit.plt where there's a jump to the exit routine, and now, since we hijacked that, it's moved into our stuff, D05C. And D05C is here, so it worked. We've jumped up to here. Now I can just do step through all this. So if I just continue now, it runs, it exits normally, it doesn't crash, it did the exploit, and if you quit, you can now do ss-pant and see that you now have a process listening on port 4444, which is what it does. Now anybody can take over this box by doing a netcat to its address. I'm going to use the loopback on one machine, and then port 4444. Now I have a shell. I can do who am I and IP address. I can execute commands here. And when I exit, that's going to end the connection. Now I saw questions go. A question: will you have a chance to update the Python code samples? Yes, I already did. Yes. So and I'm glad you asked it, so I can make sure I made this clear. I changed it so this points to the Python 3. If you go to 204, it's now 204E. This is the Python 3 version. And it's got the Python 3 code. If you want the Python 2 version, it's here, but I don't think there's any reason for anybody to use that anymore because Python 2 is over. So I updated 204, 205, and 206 to Python 3. So yeah, that's very, very much better. Good? All right. So that's the point. That's why it failed. And I've seen this happen many, many times. Metasploit shellcode is pretty fragile. I think all shellcode is pretty fragile. And there was nothing wrong with the process. I just got unlucky with my shellcode. Although there is a little curiosity, which would be kind of interesting. Apparently, there's a pattern of bytes that you can't print with the printf statement in C. And that kind of suggests if you wanted to get fancy, there might have a bug in a C library function. Maybe it's even exploitable or something. I kind of doubt that, but anyway, there's an area of research I did not explore, but it might be fun to fuzz the printf function and try to find out why it's crashing. Anyway, that's the first thing I wanted to show you, to pick up what I had left over from last time. So I think I'll stop this video and make a separate video